All right, folks, let's get to getting. So today we're going to introduce the concept of symmetrical components. And the whole purpose of symmetrical components is to take systems that are unbalanced only at one point, okay, at one point location, and make those systems more balanced. And so we don't actually use the term balance because balance is when you have exactly the same magnitudes, but the phase shifts are 120 degrees. So that would have it to be a balanced system. A symmetrical system can be balanced, but it will have one additional system that's going to deviate from our concept of balance. So we can't call it balanced. We'll call it symmetrical or equivalent, if you will. So we're going to brace systems that are not perfectly balanced, and we'll break them into symmetrical components. And then we're going to develop these networks, positive, negative, and zero sequence networks for power systems. We started talking at the beginning of the semester when we talked about phase rotation. We said ABC, or positive sequence rotation, or then ABC, which is positive sequence, or ACB, which is negative sequence rotation. So you'll see, hopefully, where those terms come from when we actually start to cover here. We don't talk too much about zero sequence in terms of rotation because there isn't actually any rotation. Those are fixed. And the reason why it's really helpful for us to understand positive, negative, and zero sequence, because if you do any protection whatsoever, a lot of the relays that you have actually will use positive, negative, and zero sequence components to make determinations about tripping or not, or maybe even alarming. And so modern protective relaying is basically a computer. It monitors the phase currents, and then it does calculations internally to figure out the positive, negative, and zero, and then it sends them to the right locations for decisions to be made. All right, so the grounding is now a serious item to consider because it will tell us, do we actually have the capability for ground current to flow? When do you have ground current flowing, or the possibility of ground current flowing? When there's some sort of a connection to ground. So you need to really think about delta Y transformers and whether that neutral is grounded or not, because if it's not grounded, you don't get ground fault current, right? Especially for the first fault, when we only, and these systems are only talking about the unbalance at one location, so we don't have multiple faults. We just have a single fault. And so if a system is grounded or not tells me, will ground fault current flow? Now, based on that, would you think grounding a system is good or bad? If you ground a system and then someplace else on the system, a wire comes into contact with ground, then you get a current flowing through ground. What if you're the person that touches that wire and connects to ground? Is that a good thing or a bad thing? Bad for you, yeah, really bad for you. So do you think having a system that's grounded is a good thing or bad thing? Based on that one circumstance, it might be bad, but it's actually a good thing. Because if I have a system that is ungrounded and that first ground occurs, no big deal, right? Nothing happens. I don't get electrocuted because there's no complete path. The problem becomes when there's a second ground that occurs. When the second ground occurs, now you have a lot of fault and you can't, and then you trip. And so what happens, the reason why you want to have a grounded system is it allows you to detect that a ground has occurred on the system because it causes a trip. So knowing a ground exists, you would prefer for there not to be a ground, but at least being able to identify that a ground has in fact occurred is pretty important. And since again, these systems are designed to operate 50, 60, 80, 100 years, grounds are inevitable. And so isolating the grounds before you get that second ground really helps provide a much more reliable and safer system. So it used to be in my house, I have a house built in 1941. They didn't have grounded outlets. You could see two-prong outlets everywhere. Now everything is a three-prong outlet because you have an earth ground that goes to the appliance that you're using, but the neutral is also connected to ground as well to enhance the safety. So that's why we actually want grounded systems. Positive and negative sequence are perfectly balanced systems. So at the neutral, when I have the three currents, right, going here, the sum of the currents for positive or negative are always going to be equal to 0. So the current going through here, why isn't that writing? Oops, what's going on? The current here, oh boy. I don't know why it's not working. Sorry, folks. It's like the computer is falling asleep. So the positive in sequence current is always going to be equal to 0. So that's a really important thing, because I don't care what the neutral is what that tells me. If there's a connection to neutral or not under positive and negative sequence, it doesn't matter, because those currents are always going to sum to 0. But the ground current, the 0 sequence current, we'll see how that has to flow through ground. So you only have a ground fault current or a 0 sequence current if you have a ground connection. If you have no ground connection, you would just show that impedance as an infinite impedance or an open circuit, right? So you're going to be making these networks, positive, negative, and 0 sequence, and you're going to have to append on this additional information about, hey, what type of connection do I have? The ground only impacts the 0 sequence network, doesn't affect the positive and the negative, so you don't have to worry about that. So up until this point, right, we've always assumed that our voltages are the potential difference between a phase and ground or neutral. And that means that's our 0 voltage point. So ground or neutral is our reference connection. And so everything we go is actually in there. It doesn't actually have to be the physical ground that we're standing on. What if you're on a boat, right? You're out in the water. The water itself isn't grounded. You're not hanging a wire from behind you trying to get grounded into the ocean. That doesn't really do anything for us. So the idea is that it could be just a structural steel, like your car, for example. Your chassis in your car is grounded. And so if you'll notice, you'll see some of the systems that you'll actually run a fairly large conductor that goes to the chassis ground. And that can't be painted because paint is an insulator. And so you'll actually see some grounding connections on the chassis. So your car is a perfect example of that's your ground. An airplane is even obvious, right? Because you're up in the air and you have no connection to ground because you're floating in the air, essentially. So it doesn't have to be an actual ground. It could be just, whatever metal frame that you're on. So when we're balanced system, right, all 3 phases have the same magnitude or are offset by 120 degrees, then there is no neutral current, none whatsoever. So you don't even need a ground connection. And ideally, we're trying to run a balanced system. So we're trying to achieve that. When you're talking about transmission or distribution, transmission, typically you run almost perfectly balanced. You get as close as you can. In distribution circuits, it almost never is. It's too difficult to make it. But we're focusing more on the transmission system. The distribution system, I had a student who's taking this class online stop by and take a look at a book on how to actually analyze unbalanced distribution systems, and it's a lot more work. And so that tends to be a graduate level course. But for undergraduate level course, we can assume that the systems are fairly well balanced. So we have the reason for grounding is safety. It's way safer if you have a grounded system, because if a conductor comes into contact with ground, then that trips the breaker, as opposed to it starting a fire or anything like that. It also provides equipment protection too. So when you walk up to a piece of equipment, the case should be grounded. For those of you doing your senior project, if you have a metal case, you darn well better make sure it's grounded to what your circuit's at, because you could come up and touch it and you could electrocute yourself, right? You could provide that path. So how do you get around it? You don't want to worry about the ground? Put it in a plastic box. Anybody here doing any electrical installs in their lives? If you look at the electrical boxes that they sell at Home Depot or Lowe's or whatever, there are a lot of blue or gray plastic boxes. Those are insulators. So it used to be with the metal boxes, you had to ground the box because you could come into contact with some metal and you could actually conduct electricity. So those actually had to be grounded, again, to cause the trip before you came into contact with it. But the new blue plastic or gray plastic boxes, they can't conduct electricity, especially for household voltages that we're talking about. So you don't need to worry about it. So you always want to ground things for electrical safety for you and to make sure that the equipment is protected. So you don't have an arcing thing in your system kind of causing problems. It trips the breaker immediately. And we've already gone through a little bit and talked about the different types of faults. The balance fault is the least common of the bunch, but the other three that we have here, single line to ground, a line-to-line fault, and a double line to ground, all three of those are unbalanced faults. There's also an open conductor, which is basically that the two other phases are energized and the other one is broken for one reason or another. We're not going to analyze that. It's essentially similar to a line-to-line fault is how you would do that. So we're going to focus on single line to ground, line to line, and double line to ground. And symmetrical components only works if the system is unbalanced at one point, which is where the fault is going to occur. All right? That's particularly important to us. All right, so now we're going to go ahead and introduce the concept of symmetrical components. And this is based on a lot of math, but you can decompose vectors, right? Just like Cartesian coordinate system. If I go three-dimensional, I have an x vector, 1, 0, 0. So that's my x vector, my y vector, 0, 1, 1, 0, 1, 0, and my z vector, 0, 0, 1, right? So to go anywhere in 3 dimensions, I just need those 3 basis vectors. Do you all remember basis vectors from, what is it, 258? The linear algebra portion of the linear algebra and differential equations. The basis vectors are like the absolute base vector you can get to recreate another set of vectors. So Cartesian coordinates is the perfect example. In symmetrical components, we also use our basis vectors, and they're going to be broken up into 3 systems: positive sequence, negative sequence, and 0 sequence. 0, 1, and 2. That's how we denote those. And that's common around industry. So if you were to open up a Schweitzer Engineering Labs relay manual, you would see how they would polarize on I or V2, which would tell that it polarizes on negative sequence voltage. It actually needs that voltage to be able to make a decision about stuff. So we've already been doing positive sequence. That's ABC rotation. So this is ABC. Negative sequence is ACB. And 0 sequence, as I mentioned at the beginning of class, has no rotation whatsoever. It's just, they're fixed in their position. So here's our positive sequence. We have ABC rotation. Do you all remember ABC rotation from the beginning of the semester? I hope so. What does it mean when you say ABC rotation? Tell me more, Mason. That's a balanced system, but what makes a balanced system ABC rotation? Well, it wouldn't be on the device. It's actually how the phases are rotating, right? But the way that you can tell here, remember, I put my eyeball on the x-axis, and I start with A. So A is the very first one. That's my reference. And what's the next vector that I see? What phase? B, right? Because it rotates in a counterclockwise direction. So A is the first, because that's my starting, my reference one. Then I see B, and lastly, C. So positive sequence is ABC rotation. All right? That is the definition of how we get those vectors. Negative sequence is exact opposite. Because I'm looking over here and I see A first, because A is my reference, then I see C, and then I see B. This is negative sequence. Why do you think we call it negative sequence and positive sequence? Any ideas? Yeah, because if I go back to positive sequence and I flip the rotation around, what's the order that I get? A, C, B. So negative sequence is called negative because now those vectors are rotating. The positive sequence vectors would be rotating in the opposite direction. And some of the things we'll talk about, well, we may talk about, I don't know, in protective relaying, is you have these things called double frequency, because if I have 60 hertz going this way and 60 hertz going this way, then the relative speed of those two is 120 hertz, right? Because one's going this way at 60, one's going this way. So the relative speed is 120. So you'll actually see, they call them double frequency components when you talk about negative sequence rotation. So you actually get 120 hertz. So here are the three vectors. I have positive sequence, I have negative sequence, and I have zero sequence. We talked about positive and negative having the same magnitude and offset by 120 degrees. What do you notice about negative zero sequence? Same magnitude and all the same magnitude, and the angle for A equals the angle for B equals the angle for C. So they're not balanced, right? They're exactly the same. So for zero sequence, the magnitude and the angle for all three of those, right? EA, EB, and EC are all exactly the same. Do you have any guesses as to why perhaps that would be that way? I kind of gave you a hint at the beginning of class. What did I say about the current that travels in the neutral for positive sequence? How much current goes in a positive sequence system? What current goes to neutral? Zero, because it's balanced, right? Kirchhoff's current law says the sum of the currents into the node equal the sum of the currents out of the node. Well, the positive sequence currents cancel each other out because of the same magnitude, offset by 120 degrees, right? There's one vector plus the other vector plus the other vector. Sums to zero, right? So if I want to be able to get a ground fault, I have to be able to get current flowing through the neutral. Over here, with zero sequence, I have that one, plus that one, plus that one. Does that equal zero? Doesn't look like it. Looks like something that's 3 times any of the base magnitudes, or the base quantity. So zero sequence can't be balanced because you would not have any ground current. And so that's why they're the same magnitude and angle. So again, not balanced, but symmetrical. These are all symmetrical. So we use the term symmetrical components and not balanced components. So here's how you can go ahead and rebuild. So this is our set of original 3 phasors. And you can see they're not balanced, right? Because this is I, we'll call that IA, IB, and IC. And you can see the magnitudes are all different, as are the angles. But those have been decomposed into a positive sequence, a negative sequence, and hard to see, but a zero sequence there. And you can see each of the components for each particular phase. Again, in positive sequence, look at the magnitudes. They're all exactly the same, aren't they? Look at the angles, 120 degrees apart. Same thing for negative sequence. Magnitudes are the same. Angles are 120 degrees apart. Zero sequence, I only show the one. So if you look, and we'll actually do this here. So this is that same system, whoops, that we just looked at. So here's input, positive, negative, and zero. So this one you can actually just drive. So let's make this one kind of long and crazy. you can see that that's not balanced, right? Look how wacky the red phase is. It's magnitude is much higher, 3.5 versus 1. And the angle, there is no 120-degree phase shift there. But take a look at the addition here, right? You can see this is positive, negative, and 0. So if I add the positive sequence, why isn't that turning on? If I add the positive sequence of the red, the negative sequence, and the 0 sequence, I am going to rebuild that original phaser. So let's take a look. Let's clear that. Close this out. And I'm actually going to show the superimpose. And you're going to look closely. If I hit the right button. Why isn't it showing superimpose? Whoops, it seems like it locked up. Hold on. So now I'm not even showing the positive, negative, and 0 parts on separate diagrams. I'm actually showing them here. And if you take a look, it might be a little hard to see. So we'll highlight it. This here, this red line matches the magnitude of here and here. Right? So you can see that their magnitudes are the same and they look like they're 120 degrees apart. So then I'm going to add to it the negative sequence. And again, those are 120 degrees offset. And then I'm going to add my 0 sequence, which is here. Oh, I can't really see it all that well. If you look closely, actually, I think I grabbed, let me back up because I think this is the, let me do that again. So this is the positive. The negative should be this one right here. So that should be here. And here, and then the 0 sequence is this one. It's kind of hard to see. This I'd have to drag it out of the way a little bit. Let's see. Oh, wait a minute. These is, oh, okay. Let me show you the one more time. Sorry. Getting the order of these is kind of important. So here's the positive. Okay. The negative is here, here, and here. And if you put those all emanating from a neutral, you'd have all those values. And then the 0 sequence is this one, and this one. So you can see them all put on top of each other. But what's cool about it is the reds added together give me my original phaser. The blues, let's call that phase B, or IB1 plus IB2 plus IB0 makes our blue vector, original blue vector. And the same thing for the yellows. We get those individual ones added together and we get the results. But if I switch back to showing them as separate, so I'll clear this. Those actually become, showing them they're all balanced, right? Positive, the positive and negative are balanced, and the 0 sequence are all the same. Again, you only see the yellow one here because they're on top of each other, right? So you just see the one vector looks like it's more the yellow one because that's the last one that they plotted. All right, so that's how we're going to go ahead and build it. So to build this vector right here, the yellow one, I add this part. So we'll add this one, and then I'll try as much as I can add this one over here. And then I'll add this one over here. And that should be, if I can draw, about the same, or it should be exactly the same if I add them and get it that way. Okay? So that's what we're doing with symmetrical components. We're just breaking them down into two sets of balanced and one set of symmetrical phasors to rebuild the original ones. And you'll see why that's important to us once we start doing more of this. Oops, come on, go back here. So if anybody wants to play around with it, you can go to this website, blair.github.io/sequence, and you can play around and you can see it on a bigger screen. It's pretty basic, but it does a really good idea because you can create any one that you want. All right, so now let's do the math. Let's add them up. Phase A is going to be IA0 plus IA positive plus IA negative. Phase B is the same, but all subscripted B. And phase C is the same, but again, all subscripted IC. So I've got the negative sequence set. I've got three vectors for that. The positive sequence set. And the negative sequence set. So you can say, Paul, wait a minute, this is a lot of work. I have 9 different terms that I need to calculate. I only had 3, but now I had 9. Is that really going to be saving me some time? Well, do I really have 9? Let me dismiss that. Nope. I don't have 9, right? Because IA0 equals IA1 equals IA2. So instead of having 9, now I'm down to 7, right? And I wonder, IB1, does that look like IA1 at all? Doesn't look like it exactly, but it's close. What do I need to do to IA1 to get to IB1? Let's do it on whiteboard over here. This is IA1. IB1 is down over here. What do I need to do to IA1 to get to IB1? Magnitudes are the same. What about the angles? There's a phase shift, right? A phase shift of 120 degrees. So what do I need to do to IA1 to make it become IB1? Not a tough question. I have to phase shift it by 120 degrees. What do I do to the magnitude? They're the same. So if I multiply that by 1, magnitudes are the same. How do I phase shift it? I just make a complex number and I phase shift it by negative 120 degrees, right? So IB1 is equal to IA1 multiplied by 1 at an angle of minus 120. And IC1 is also equal to IA1. But it's just times 1 at an angle of positive 120. So all I need to do is solve for IA1, right? Because I can get the other two by just multiplying by 1 at an angle of 120 and 1 at an angle of minus 120. So my 7 has now gone to 5. Do you think that that's also the same thing when I do B? I mean, the negative sequence? IC2 and IB2. Sure looks like it. It's the same thing. IB2 is equal to IA2 multiplied by 1 at an angle of 120. And IC2 is equal to IA2 times 1 at an angle of minus 120. So all I need to do is multiply that. So now my 7 or my 9 that went to 7 went to 5 and now is at 3. So all I need to calculate IA0, IA1, and IA2, and I can calculate all the other symmetrical components just by phase shifting. Because IA1 and IA2, I mean IA1 and IA0 and IB0 and IC0 are all the same, so there isn't any work there. So this is huge for us because I don't actually have to do all those calculations, and because I'm dealing with a system that is balanced essentially in symmetrical component land, then I don't have to worry about, adjusting and keeping track of each individual phase. I can do the per phase analysis that we've been doing up until this semester to get the results that I need. So symmetrical components convert these systems that are unbalanced into a balanced set of systems so I can do per phase analysis. All right. So we've already talked about just having to calculate IA0, IA1, and IA2. That formalizes that over here. You can see that IA is just equal to the sum. And IB is equal to all the B components. But we already said that I can get the B components by taking the A components and phase shifting them. That's what that matrix here says. Now, where does alpha come from? Alpha, or A, is 1 at an angle of 120. Alpha squared is 1 at an angle of 120 times 1 at an angle of 120. When we do complex multiplication, multiply the magnitudes and add the angles. But this is based on a 360-degree circle, right? So isn't 1 at an angle of 240 also equal to 1 at an angle of minus 120? And what do you know? This right here is alpha squared, and this is alpha. So anytime I see, that's alpha squared, anytime I see that 1 at an angle of 120 or 1 at an angle of minus 120, I can substitute an alpha. So I now have created a matrix. So I've got my 3 A-phase symmetrical components, and then I have an A matrix. We're going to call this the capital A matrix. Highly suggest to do this homework and work, you put this in your calculator and store it. Or if you do MATLAB, you go ahead and store it as your capital A matrix. So you can have your little a, if you want to call it little a instead of alpha. I don't have a particular preference. And then you want to have a capital A, you would go ahead and specify it that way. So here's our A matrix. Now I can do everything in terms of matrices. So my I matrix, which this matrix is called my phase matrix, is equal to A times my symmetrical components matrix. And then I can do one more step. I'll get rid of all the A's because I'll just assume that we know it's going to be the A phase components I'm calculating. And then my phase components is going to be equal to my A matrix, my capital A matrix, times my symmetrical components matrix, the IS. So I can go back and forth just by using linear algebra, right? I can go back from phase components to symmetrical components, or I can go from symmetrical components to phase components. And my A matrix, if you invert it, this is the A inverse matrix, right? This is not a new matrix. It's just the inverse of A. So if you plug that into your calculator, you're going to get the 1/3 multiplied by all those terms. Now, why is this so important to us? Why is this particular equation incredibly important? Well, do you remember how I talked about relays today? They can do calculations to figure out the symmetrical components. In the real world, I have a wire with 3 currents going into it. This is phase A, this is phase B, and this is phase C. If I can measure those currents, stuff them in a matrix, then the relay, the relay can actually calculate all those symmetrical components. So the symmetrical components is just a math conversion. It's like Laplace or Fourier, where you convert it to a different domain. That's my domain. I'm in symmetrical component. We'll call it land for lack of a better term. But now I took my phase currents and converted those to symmetrical components. So now I can start analyzing the systems. Now I can figure out, hey, what's my zero sequence current? Do I need to trip on that? What's my negative sequence current? Do I need to trip on that? And there are cases when you actually trip on zero sequence and negative sequence. Negative sequence tend to be unbalanced. The degree of unbalance is indicated by the negative sequence, and the ground fault is indicated by the zero sequence. So now I have my relay, and I can convert those to symmetrical components, and I can actually start to do analysis on it, or I can make decisions about tripping. This applies for voltages or currents. It's more commonly used in currents because, again, most of your protective devices are going to trip on current. You do have some like distance elements that use both voltages and currents, so you would use voltages there. And then there are some times, like if you have, it's called a neutral ground overvoltage condition. So that would look at the V0 one, but those are a lot less common. You know, those are pretty rare that you find those. Those are for ungrounded systems, essentially, or not ungrounded, potentially ungrounded systems is what I should say. You have those different parameters to be able to calculate. But by knowing this stuff, we can get a lot of information about the system and when we trip or when we don't trip. All right, so let's do some math. So I've got 3 phase currents, and they look perfectly balanced to me, right? All the same magnitude and offset by 120 degrees. Now I'm going to check my symmetrical components. So I'm going to multiply my phase components by the inverse of my A matrix, and I get 0, 10, and 0. What that is telling me, I get 0 for zero sequence, 10 at an angle of 0 for positive sequence, and 0 for negative sequence. Is that what you expect? Not a lot of energy or not a lot of understanding today. Is this what you expect? Not sure? Well, let's draw a picture. We'll call that 10 at an angle of 0. We'll call that 10 at an angle of minus 120. We'll call that 10 at an angle of positive 120. This is phase A, B, C, right? Isn't that the definition of a perfectly balanced system? Saying magnitudes offset by 120 degrees? It's a perfectly balanced system whose rotation is A, B, C, right? I see A, then B, and then C. So a perfectly balanced system that has positive sequence rotation, I darn well better only get a positive sequence set of components in there. Otherwise, this isn't right. This doesn't work. So this would be a real problem if it wasn't this way. So yeah, I shouldn't get any zero sequence or negative sequence because it's a perfectly balanced system. If we swap that around and we have A, C, B here, isn't that the definition of negative sequence? Which means I should only get a parameter in the negative sequence value. So this gives me results that I expect. Hopefully that's what you expect, but that's what I expect. All right, so now let's take a look at about voltages that are not balanced. And you can see one is got a magnitude of 5. The other two are magnitude of 8. And one has an angle of 90, which does, is 120 degrees, right? So minus 30 to 90 is 120. But then you'll notice that you have that 150 in there. That's only 60 degrees away from phase A, and it's 180 degrees from there. So if I was to draw that, I would say this is 5 at an angle of 90. 8 at an angle of 150 is something like over here. And 8 at an angle of 130 something like that over there, right? That's what the three phases look like. Clearly not a balanced set of phasors. So now I'm going to run that through my symmetrical components system. And you'll notice I get all three parts. I get zero sequence, positive sequence, and negative sequence. And these aren't currents, these are voltages. V0, V1, and V2. All right. So this is just literally entering stuff in your calculator. Do you all remember how to do that in MATLAB? I don't have MATLAB up in here. Sorry about that. I might have rebooted. But to enter in E, or A, I should say, we'll call it A. A is 1 at an angle of 120. To do that in MATLAB, it's just EXP of J times 120 times pi divided by 180. In your calculators, you might be able to just do 1 at an angle of 120. I don't know. It just depends on the quality of the calculator you have. But in MATLAB, that's how I would enter that in. And then for my big A matrix, I would go 1, 1, 1, semicolon, 1, A squared, A, semicolon, 1, A squared. And that's my little a and my capital A matrix all specified in there. So if I want to go and I've got calculations and I have symmetrical components, positive, negative, and zero sequence, I can easily go back into phase components just by multiplying by my A matrix. And again, you can see these clearly are not a balanced set of phasors. I've got 5 at an angle of 0. I've got 18 at 46.1 and 18 at minus 46.1. So not even close to being a balanced set of phasors. But you can do the calculations pretty easily yourself. Now, this last little bit here is looks like it's a lot of math, but it's really going to be very important to us to figure out what we call decoupling of the symmetrical components matrix. So I'm keeping track of everything. I'm not doing per phase analysis. I'm doing the full Monty here. And I'm going to include a neutral with an impedance, potentially an impedance to ground. So I'll just call it Zn for lack of a better term. And you can see that my IN, some of the currents at the neutral connection is going to just be the sum of the currents. And then my ground voltage relative to reference is going to be equal to whatever current I have in phase A, right? So I'm looking at the voltage from here to here. So this is my plus minus. So that voltage is going to be the current through ZY. So I need the voltage drop there. Plus, I need the voltage drop through there, right? So IA times ZY plus IN times ZN. And then I include the fact that my IN is just a sum of the three currents. So now I go ahead and set it up as an easy equation with factoring it out. So I have Z1 plus ZN times IA plus ZN times IB plus ZN times IC. Those are the actual voltages of our system with reference to ground. I do that for B and I do that for C. And you'll notice that my diagonal looks exactly the same. And then the off diagonals are just Zn. All right. So now let's go ahead and take everything into symmetrical component land. So I've got my voltage phasors here. And now I'm going to start converting things to symmetrical components. So I know that V equals Z times I. That's Ohm's law. My voltage in phase components is going to be equal to my A matrix times my symmetrical components voltage. And the same thing for current. So now I'm converting phase components, or getting ready to convert those by multiplying by ABS. It's still phase components, but I've just substituted in what my symmetrical components matrix would be. And then I do the same thing for my currents here, right? So I got A times VS equals Z times AIS. I'm trying to solve for my symmetrical components voltage. So I have to multiply both sides by the inverse of A. All right? And what I end up with when I multiply these three together, in my phase A, I have zy plus 3zn. Phase B, I have zy. Phase C, I have zy. But look at these zeros here. These zeros have indicated, because remember, this here is going to go ahead and give me Vs times Is. So Vs for phase A, if I multiply it out, is going to be equal to Zy plus 3Zn. All of that times my phase A symmetrical components value. But I've got 0 times IB and 0 times IC. So I've just decoupled the networks. I don't care what's going on with B and C. I'm only interested in A. So this shows your decoupling of symmetrical components. They have nothing to do, phase A has nothing to do with B, and B has nothing to do with C, and on and on and on. Okay? So again, that's really good because the symmetrical components will be able to live in your system until there's a fault where they get connected. And we'll see that when we start going. So here are our three sequence networks. We have 0 sequence, which has our 3 times Zn in there added in, which is 3 times the neutral impedance, which is important to us. Why is it 3 times the 0 sequence? Because again, I have going through my neutral, I have 3 currents going through there. So if I want to get the voltage drop, I can either go V, we'll call it neutral, is equal to IA 0 times Zn plus IB 0 times Zn plus IC 0 times Zn, right? That's the way I'd write it out. Or recognizing that all 3 currents are the same, I just have 3. So that's where the 3Zn comes from. I get 3 times the impedance, which is how I have my impact. So this is a really important thing for us. The impedance that you pick for your neutral connection, you actually represent that by 3 times that impedance in your symmetrical components representation. It's not Zn, it's 3 times Zn. And then the other ones are just Zys and Zys, right? Because again, we don't care about the neutral. There's no current flow in there, so there is no Zn component associated with it. So now we're going to go ahead and sort of expand a little bit into those sequence diagrams. So we already talked about we have positive, negative, and 0 sequence diagrams. So now we're going to go ahead and start identifying what those positive, negative, and 0 sequence diagrams look like. For generators, when we build generators, we recognize that the system should be as perfectly balanced as possible. Does it make sense to make a generator that puts out non-balanced systems, non-balanced voltages? Definitely not. It does produce power, but it doesn't produce unbalanced power. So we're going to put a voltage source in only one network because it's producing balanced voltages. It would have to show up in multiple networks if it was unbalanced. But since we spent a lot of time and money designing a generator to make a perfectly balanced output, we're just going to show our voltage source in our positive sequence network. You could show it in the negative sequence, but most of the time, we only show it in the positive sequence. And this power source is going to be the source of energy for our entire symmetrical component analysis. We only have power sources in generators. You could possibly have it in motors, but again, those tend to just dissipate very quickly. So oftentimes we neglect those unless it's a synchronous motor, and then we would just have a back EMF. Like when we did the fault analysis with the superposition, when we did that last week, we actually would put a voltage source in there. So if you're going to look at unbalanced faults with systems that have large synchronous motors, then we would also include that back EMF voltage source in the positive sequence diagram. Negative sequence diagram just has one impedance. The zero sequence impedance has 3 times Zn. And again, we keep doing a callback to this, right? So this has happened multiple times. But where do we get these impedances from? Well, we can see that our positive and our negative sequence diagrams, those are equal to our direct axis subtransient values. Remember our direct axis quantities when we looked at those generator data sheets? That's XD. And then we're picking the subtransient value because that's trying to get the worst case fault out of the machine. That's what the machine is able to bruise out of the worst case. It's not necessarily going to be what has to be interrupted, but that has to be when it's there. That Zn, again, if you remember, here's our generator, which has 3 leads coming out of it. And this could be either solidly grounded or grounded through some sort of impedance. Do you remember the Dolby Hydro one when I said, don't worry about the neutral connections? Those were actually grounded through a transformer, right? What does a transformer do? It reflects the impedance through the windings of the transformer. So if this is a, we'll call it a 1247K to 240 volt, then if this is a 10 ohm resistor, that 10 ohm resistor is going to have a much higher impedance on its high side because you're reflecting it to the high side, so the impedance is increased. So by far, what's very common for generator protection and grounding is you have a step-up transformer, and then you have just a baby resistor, just a regular old resistor that can handle 240 volts. So not one of those quarter-watt resistors that you find in the lab, right? You're going to have some power and some voltage across it, but it doesn't have a lot of power. But the impedance gets stepped up quite a bit because of the transformer. So if you were to go to a generating facility, a lot of times what you see is one of those pole-mounted transformers. It's, you know, gray and it looks like a trash can. Those will actually be located out generators, and they'll step that resistor up, which, you know, has to have some power dissipation. So maybe it's 500 watt or something like that capable, but it actually is going to be stepped up to a much higher voltage. It's not often that you see a resistor directly in the generator, unless it's a low voltage generator. Then it's a little bit different. All right, this is the hardest part about the class, or today's class, in my opinion. And it's deciding the transformers, what impact the transformer has on your sequence diagrams. We'll start out with the positive sequence. So if you remember a transformer, and these are just going to be shown as windings right now. The idea of a transformer is whatever flows in the primary winding of the transformer, the projected or transformed vector has to flow in the secondary. So if I've got a current flowing through here, I darn well better have equivalent current to that, right? That's what a transformer does. It's got current going in the primary winding. It uses magnetics and gets the current flowing in the secondary winding. So if I have a balanced set of three-phase phasors, I have 3 currents, all with the same magnitude and offset by 120 degrees. So if there is a neutral connection here or not, it doesn't matter. I couldn't care less if there's a neutral connection. Same thing for a delta transformer with a Y winding. This current over here, it's got to flow here. This, well, I kind of did it. Let me try to do it a little bit better. That current here has to flow here. This current has to flow here. And this current has to flow there. So notice on the delta, there's no neutral connection. But on the Y, there is a neutral connection. But the currents can still flow, right? You can see that those currents are balanced. They're going to always sum to 0 at the neutral connection. So for positive or negative sequence diagram, when you come to a transformer, you just show its leakage reactance in the diagram. So when I do positive or negative sequence, all it's going to do is look like this. Just looks like plain old system. The much harder one is the 0 sequence. Because the 0 sequence, because Zero sequence all have the same magnitude and angle, right? So if this has a neutral connection or not, if that connection is open, if this is I0, IB0, and IC0, if that connection is open, these currents can't flow through there, can they? Because Kirchhoff's current law says the sum of the currents into the node equal the sum of the currents out of the node. So no current out of that node. So this impedance acts like an infinite source. There is no connection. So you can't actually have current flowing through ground. So when you have a delta Y transformer or YY, you better have neutral connections or your zero sequence current can't flow. Over here, if it's Y grounded on both ends, if I have a zero sequence, it flows through here, and then that current has to flow up, and then it distributes through there. So if there is zero sequence current flowing in a Y grounded Y transformer, then that zero sequence current has to pass through. It can't go back to where it came from. It's got to pass through and continue on to the load. So if you have a system with a grounded Y transformer, that actually doesn't help you in terms of isolating your grounds. It actually sort of connects them through the zero sequence line. So in distribution circuits, you see this all the time, but if you work at a transmission system or if you're a generating facility, you never see grounded Y transformers because it just makes things very difficult to protect and coordinate. Here's a diagram for all different types of transformers. So let's look at a grounded Y here. Can I get zero sequence current flowing on that side? Kirchhoff's current law would say, sure. If I've got current, there's a path for this neutral. Here's the problem. Is there a connection to neutral over here? Nope. So as a result, if current on the primary side requires current flow on the secondary side, but you can't get current flow on the secondary side, that means that this transformer has an open or an infinite impedance for ground current to flow through. So ground current cannot flow through the transformer. You can show the impedance of the transformer connected to the winding that has the ground, but no current can flow through there. Okay? This is a block. Doesn't happen. And I've never personally seen a grounded Y and then non-grounded Y transformer. I've just never seen it. These are all over the place on distribution systems. And what I see is current flowing through here. You can flow through here, right? Because this current goes here and that current goes through here, but it doesn't return back. So that current just blows through and continues on to wherever the load is. So if you have a grounded Y transformer on both sides, and if you have a ground, let's say someplace over here, that might not actually be able to get picked up as a fault. So unless you have a ground on your system, that system is technically considered ungrounded because there's no path for that to go back. Here is by far the most common one that you'll see in transmission systems and generating facilities, because let's check. The current can flow through here, which means it flows through neutral, right? Wait a minute, Paul. You lied to me. You said that current can't flow on this one, can it? There's no neutral on the delta side, is there? So does that mean zero sequence current can't flow? That's what that means? All right, one brave soul. Well, this current here, let's call it 1 at an angle of 0. That's 1 at an angle of 0. We'll do everything in per unit, 1 at an angle of 0. That forces a current into those secondary windings, right? Like this, and like this, and like this. This current, we'll just call it per unit, 1 at an angle of 0, 1 at an angle of 0, 1 at an angle of 0. Is Kirchhoff's current law satisfied? The current into the node is 1 at an angle of 0. Does that equal the current out of the node? Sure does. How about over here? One at an angle in, one at an angle out. Sure does. And sure does. So this transformer is the best, at least in my opinion. Why is it the best? Because it allows zero sequence current to flow, but it doesn't leave. Because Kirchhoff's current law, if I wanted to get some zero sequence current, let's say I wanted to get 0.1 at an angle of 0 going through here, Kirchhoff's current law is no longer valid, is it? Because I only have 0.9 going over here, and that would not match that current that I have there. So when you use delta Y grounded transformers, it isolates the ground because the current here is going to flow back to the source. It's going back in that direction. On the delta side, it circulates. So a grounded Y delta transformer is a perfectly fine grounding transformer, and it isolates the ground on either side. This is the best from a protection perspective because I can set my devices very sensitively to monitor ground fault current on one side of the transformer because that ground current doesn't continue on. So I can set it very sensitively because I've isolated my ground zones. And that's why for transmission systems, that's all we use. Because if you have 1 amp of ground fault current flowing, like 1 amp of per unit, whatever per unit equivalent current, it might be 100 to 200 amps of ground fault current flowing, you trip. I don't need to coordinate with downstream elements because that ground current only exists between the two delta Y transformers. B, what do you got?
Yeah, after my question, I was about to ask why.
Yeah. See, I'm a mind reader. But that's super duper important. And if you remember, when we looked at our power system for Dolby, right? We saw some delta transformers. We did see some delta Ys. But if I used to be able to show you in the real world what we had, diagrams, you'd only see delta Y transformers. Do you all remember our transformer test data sheet? What kind of transformer was that? 60, 80 MVA, 35 kV to 115 kV, I believe is the rating. What were the windings configured? Anybody remember? Anybody? I could be BSing you, right? Let's see. Let's go here. Remember the 100-page document? Let's see. Whoop. Connection. Y delta. So as long as the owner of this facility ran the neutral to the Y, that's exactly what they have. And if you look back, I jumped ahead a little bit, but if you look at here, it doesn't really show. Well, we'll zoom in a little bit. But if you look closely, here's the transformer. Can you tell? Whoops. Can you tell which is the high voltage winding and which is the low voltage winding? Look at the spacing on this side of the bushings compared to over here. This is spaced out a lot more than over here, right? So it's reasonable to assume that the H windings would be the high voltage windings, the high voltage bushings. Look at the neutral. There's an actual connection to ground right here. So that's how most generating stations are built, to be grounded. And the transformers are almost always solidly grounded. So that backed us up. Last two, delta ungrounded Y. At that point, there's no connection for the Y. So it looks just like this one. That ungrounded Y really dictates a lot what's happening. And a delta, this is the wackiest one. If there is zero sequence that makes it inside the transformer somehow. I don't know how it's there. It can circulate inside the transformer, but nobody can enter and nobody can exit. So you saw your zero sequence that allows you to circulate inside the delta, but nothing entering or nothing exiting. So when I show my impedance, I'm actually showing it there. Because I know you all love information, I added this on, which has a few more. So 3-winding transformers. You can see the 3-winding transformer and its zero sequence connection. You can see the 3ZN, right? Then you actually have another 3-winding transformer. You have 2 grounded Y windings and a delta. Again, you can see the neutral connection up above. So I should actually add this. That's positive and negative sequence. So the transformer is a transformer. The zero sequence, you can actually see the 3Z end. So that actually allows, because the delta can circulate. If you have grounded over here, it's basically the same thing. If you have one ungrounded, well, that's still okay because I can circulate over here, right? And I've got a connection over here. And then the last one is if I have an auto transformer with a buried tertiary means the delta winding is not coming out. You can see that I have one connection over here. And then if I have a couple of different designs, this is called the zigzag transformer, which introduces this additional impedance. You start to see more zigzag transformers for grounding purposes. A lot of systems for photovoltaic, like 5 megawatt or less facilities, they like to use these type of systems and they work pretty darn well. So this is probably more than what most of you will ever need. This diagram here is the most important one. And this is really important because when we start looking at building sequence network diagrams, so one of the homework problems you're going to do is you're actually going to go back and look at that Dolby system and build a positive, negative, and zero sequence diagram for that system. For the positive and negative sequence diagrams, it's just really simple. Don't even care what the neutral connections are. For the zero sequence, you're going to have to look at these diagrams for the transformers and the generators and make sure, are they connected to ground? Will they allow ground current? And so drawing the zero sequence diagrams tends to be the most amount of work, the hardest to do, the hardest to configure. Questions, because we went through a lot, very important stuff. But it really is, again, it's really important to figure out how do our systems actually get grounded, why are they grounded, and why are they configured this way. And it's because of this zero sequence. And again, the reason why we talked about a distribution circuit. So a distribution circuit, right, might have a Y ground, if it's like for a Walmart, essentially. So a Walmart usually has a Y grounded like that. So this is 480 amps, 500 MVA, or 5,000. No, it's 5 MVA, decent sized transformer. The reason why they do that is because 5 MVA, what are you talking about for a current? Not very much. So if they have a ground, they'll just rely on the phase elements to trip it. So if you have a fuse, the fuse will trip it off. So distribution circuits, you don't worry too much about ground because most of the time your individual loads are going to be like 30 amps or less. So you don't even care about the distribution ones. At the substation, the substation transformer, so this would be like a 5 MVA, the substation transformer, those would be configured like this. This would be the 35, or if it's Versant territory, this would be 46 kV, and this would be 12.47 kV, and they would have a delta Y there because they're trying to isolate sub-transmission and distribution in terms of the protections that they have. Okay? But again, this is hard material in some respects, but it's real world. This is exactly what the system is configured. These are all how these systems are set up. Questions? Thoroughly confused? TV land's awful quiet. Any TV land questions? There's a whole gaggle of you on there.
None here.
I know my friends who work for power, Now maybe they're trying to say, oh, I remember seeing some of these. And I would love, love, love to share actual diagrams of one-line diagrams of systems. But a lot of that stuff has become CEII, all protected information. So you don't have the ability to share it. But it used to be like when I taught this class, maybe 7, 8 years ago, I used to bring up Aspen one-liner models of the actual New York ISO New England system. We'd actually look at it, we'd look at transformers. But you can't do that anymore. It's called critical energy infrastructure, CEII, critical energy information or critical energy infrastructure information. That's what it stands for. And it's not like government secret, top secret stuff, but it's kind of becoming that way. So you can get into a lot of trouble. I don't think you can get into any criminal trouble that I'm aware of, but I don't take a chance. So I can't put that information up anymore, unfortunately. But if you scrounge around and look around, look at some of the transformers, you might be able to see how some of those are configured. So any questions? No questions? Completely ready for processing information? All right, if there's no questions, have a wonderful day. I will see you all on Monday, right? Take care, everyone.
Thank you.